All right, chapter number 7.1, what are redox reactions? So would you already understand that the word redox is a simultaneous combination of oxidation and reduction reaction? Now we define oxidation in many different ways, right? But we actually only took up on two ways previously, ठीक है? हम सिर्फ दो तरीकों से ऑक्सीडेशन को ओ लेवल में डिस्क्राइब करते हैं, हालांकि मल्टीपल तरीकों से डिस्क्राइब कर सकते हैं, लेकिन हम सिर्फ दो तरीके से डिस्क्राइब करते हैं, हम उसी के साथ स्टिक कर जाते हैं। आई बी वेरी ऑनेस्ट फॉर अ प्री रिक्विजिट, ठीक है? अगर आप डिफाइन करना चाहें सिर्फ ऑक्सीडेशन को, तो एक्चुअली में आपके पास ऑक्सीजन किसी रिएक्शन में ऐड होना, किसी रिएक्शन में ऐसा होना कि आपके पास हाइड्रोजन जो है वो रिमूव हो रही है, ठीक है? फॉर एग्जांपल हाइड्रोजन पहले थी और बाद में वो हाइड्रोजन अलहदा हो जाए, ठीक है? वो ऑक्सीडेशन है। ये वाली डेफिनेशन हम ओ लेवल में नहीं कराते। ऑक्सीजन का डेफिनेशन हम ओ लेवल में करा देते हैं, ये नहीं कराते, ठीक है? और आप जानते हैं कि इलेक्ट्रॉन का लूज होना, ठीक है, प्लस इलेक्ट्रॉन, ये वाला रिएक्शन कि आपके पास लेट्स से यहाँ पर Fe है और आपके पास Fe पॉजिटिव बन गया है, प्लस उससे इलेक्ट्रॉन लूज हो गया है, ये, या आपके पास ऑलरेडी वो Fe2 पॉजिटिव है, ठीक है, और वो Fe3 पॉजिटिव में चला गया है बाय लूजिंग एन इलेक्ट्रॉन। Although here ये definition सेम लगती है, but there are two perspectives to see it. Number one is कि आप loss of electron देख रहे हो. Number two, from a smaller oxidation state, you're moving on to a bigger oxidation state. Oxidation state का increase होना. These are all four types of oxidation reactions. Okay, and the exact opposite would be reduction. ऑक्सीजन का लूज हो जाना रिडक्शन है, हाइड्रोजन का ऐड हो जाना रिडक्शन है, इलेक्ट्रॉन का गेन हो जाना रिडक्शन है, ऑक्सीडेशन स्टेट फ्रॉम अ हायर वैल्यू टू अ लोअर वैल्यू मूव कर जाना भी रिडक्शन है, ठीक है? बट वी पिक्ड अप ऑन दिस वन एंड दिस वन। हम सिर्फ फर्स्ट और थर्ड टाइप को डिस्कस करते रहे ओ लेवल में। इस मर्तबा इनमें से कोई वैल्यू भी कंसिडर हो सकती है, ठीक? कोई भी टाइप ऑफ डेफिनेशन कंसिडर हो सकती है। तो गेटिंग बैक टू द बुक, हमारे पास ऑक्सीडेशन की सिंपल वैल्यू गेन ऑफ ऑक्सीजन है बाय एन एलिमेंट। किसी एलिमेंट को ऑक्सीजन के साथ रिएक्ट किया, आपके पास ऑक्साइड फॉर्म हो गया, ऑक्सीडेशन। रिडक्शन इसका एग्जैक्ट ऑपोजिट हो जाएगा, लॉस ऑफ ऑक्सीजन हो जाएगा। किसी चीज में ऑक्सीजन शामिल है, हम उसे डिस्प्लेस कर दें या निकाल दें, तो ये सिंपली वो ऑक्सीजन लूज कर जाए, like in this case copper oxide has been converted into copper, so we can easily say that copper oxide has been reduced to copper, and you'll find the same sentence over here, ठीक है? अगर हम इस इक्वेशन को गौर से देखें जो कॉपर और हाइड्रोजन के लिए दी हुई है, इस इक्वेशन में हमें ऑक्सीडेशन होती हुई नजर आती है। किसके साथ? हाइड्रोजन के साथ। हाइड्रोजन हैज बीन ऑक्सीडाइज्ड इनटू वाटर। तो अगर आपके पास साइमल्टेनियस हो रहा हो तो इसे हम रेडॉक्स रिएक्शन कहते हैं। ऑयलरी इज अ गुड वे टू रिमेंबर इट। ऑक्सीडेशन इज लॉस ऑफ इलेक्ट्रॉन, रिडक्शन इज गेन ऑफ इलेक्ट्रॉन, ठीक है? ऑक्सीडेशन रिडक्शन रिएक्शंस यूजुअली एक दूसरे को कंपनी कर रहे होते हैं। हम इन रिएक्शंस को रेडॉक्स रिएक्शंस कहते हैं। रेडॉक्स रिएक्शंस में हमारे पास बहुत सारी एग्जांपल्स हैं। फोटोसिंथेसिस है, ये फूड प्रोवाइड कर रहा है पूरे प्लैनेट के लिए। रेस्पिरेशन है, तो एक्चुअली कीपिंग मोस्ट ऑफ द स्पीसीज अलाइव ऑन द प्लैनेट, ठीक है? इसी तरह हमारे पास रिडक्शन एडिशन ऑफ हाइड्रोजन भी हो सकता है। रिमूवल ऑफ हाइड्रोजन हमारे पास इससे ऑपोजिट ऑक्सीडेशन हो जाएगा, ठीक है? हमारे पास दो तरीके होते हैं फाइंड आउट करना कि आपके पास सब्सटेंस जो है वो ऑक्सीडाइज या रिड्यूस हुआ ड्यूरिंग अ केमिकल रिएक्शन। वन, इलेक्ट्रॉन ट्रांसफर चेक कर लें। इलेक्ट्रॉन लॉस हो तो आपके पास ऑक्सीडेशन है, और इलेक्ट्रॉन गेन हो तो रिडक्शन है। और इन अदर ways simply change in oxidation number. Remember, if we're moving from a smaller to a bigger number, mathematically speaking, then we're getting oxidized, vice versa, getting reduced. उसके लिए बहुत अच्छी एग्जाम्पल्स उन्होंने प्रैक्टिस के लिए शो किए हुए हैं, ठीक है? उनमें से किसी भी रिएक्शन को आप हमेशा वर्कआउट कर सकते हैं बेस्ड अपॉन द वैल्यू, राइट? फॉर एग्जांपल हमारे पास कुछ रिएक्शंस तो इसमें बहुत आसान है, आई गेस। इफ आई टॉक अबाउट दीज, दिस one's easy, this one's easy, this one's easy, तो जरा गौर से देखें तो ये भी एक अच्छा क्वेश्चन हो सकता है। दिस इज 0, दिस इज +4, दिस इज -2 into 2, ठीक है? ये आपके पास -2 into 2 है, ठीक है? तो ये आपके पास क्या हो जाएगा? ये ऑफ कोर्स +2 into 2 हो जाएगा, ठीक है? -2 +2 इस तरह से। तो you will get to see कि changes किस में है. अगर आप और से देखें तो पता चलता है ऑक्सीजन में शुरू से तक कोई चेंज नहीं है. The basic whole reduction oxidation redox reaction is actually occurring between carbon and iodine. आयोडीन आपके पास यहाँ पर +2 से 0 स्टेट में जा रहा है और कार्बन आपके पास +2 से +4 स्टेट में जा रहा है. One of them is gaining electron, one of them is losing electron. Carbon is losing electrons, getting oxidized, and iodine is actually gaining electron, getting reduced. Okay, so you can work out these and these as well. These are good examples, by the way. You'll find more difficult examples in past paper questions. Moving on, reduction and electron transfer. Half equations हमारे पास usually लिखी जाती हैं. That is something that we have already done back in O-level for IGCSE. Half equations for either reduction half equations or oxidation half equations. We have done that in the part of electrolysis. Okay. For example, sodium reacts with chlorine to form the ionic compound sodium chloride. Here we have the equation. If we divide this equation into two separate equations, one of them is going to show you oxidation, the other one reduction. For example, sodium is losing an electron, so it's the oxidation reaction. You can show it like this, you can show it like this. Both ways are correct. Chlorine, on the other hand, is gaining electrons. It's getting reduced. It is reduction. So if we divide this equation into two exactly equal parts, it would show us that one of them is oxidation, one of them is reduction. In another example, let's take a displacement example. For example, iron is reacting with copper ions and getting displaced. You get copper ions and iron ions and copper at the end. Now you'll see that iron is losing electrons, so iron is getting oxidized. Copper is gaining electrons, so copper is getting reduced. These are kind of the displacement equations. We have done them back in O-level or IGCSE. So balancing half equations. Before we get to this part, let me explain that some things that we have already done in IGCSE. For example, if we talk about electrolysis, it was pretty simple that at electrolysis, we have had two half reactions, one of them acting at cathode and the other one acting at anode. And it was pretty simple and straightforward back in O-level or IGCSE that oxidation always occurred at anode. It lost electron, and those electrons exactly were gained at cathode, so reduction always happened at cathode. Now, in case of displacement reaction, back in IGCSE, since I've taught that back in IGCSE, so I actually revised this for A-level students so that they don't have a problem. There are actually of two types. If we talk about metal displacement, then more reactive metal displaces the less reactive one from its solid solution, maybe in the solid form, as all of this is possible. So anything can happen. But in almost all the cases, the more reactive actually gets to oxidize. It loses electrons more readily, and the less reactive one has been forced to reduce. That's what is happening in this exact reaction as well. Iron is more reactive, iron gets to oxidize. All right. Copper is less reactive, copper is forced to reduce, forced to reduce. Let me tell you, both of these are metals. Both of them will love to lose electrons. But if it's a competition between the two, like a metal displacement reaction is, then the more reactive metal gets to oxidize, and it actually force feeds the less reactive metal, which is exactly happening in this case. If we talk about non-metallic displacement, now non-metallic displacement was also a part of IGCSE. For example, I hope you remember this reaction. Cl2 was capable of displacing bromine from a solution of KBr, producing KCl, and it was producing bromine. So you see that in this specific case, non-metallic ones, the case is exact opposite. The more reactive gets to reduce, since more metals love to get reduced, and the less reactive, vice versa, gets to or forced to oxidize. So in this case, chlorine is going to gain electrons, and bromide ion actually lose those electrons to become bromine. So in this one, you can see exactly how the exact opposite of metal displacement is occurring. Okay. In the formation, these are different cases that we have already studied back in IGCSE. So formation of ionic compound. In this case, cations always formed because of oxidation, and anions always formed because of reduction. Means metal love to oxidize and lose electrons. Non-metal love to gain those electrons, become anions when they get reduced. So these are the different cases that we've already studied back in IGCSE. So there are some specific cases and some specific things happen, so you can easily remember them from IGCSE or I hope I make my point to I.
Yes.
All right, good. So balancing half equations, since we have discussed it before, it's almost the same thing, and we're going to discuss it again. When you are going to balance half equations and you are going to come up with an overall equation, what's important is that you take care of both number of atoms as well as you take care of charges or the electrons that are being fed or being lost or being gained from one side and from the other. All right. So let's talk about construct a balanced dynamic equation between nickel and iron 3 ions. Now nickel is going to lose 2 electrons and iron 3 ions are going to gain an electron to become iron 2. Okay, so nickel loses 2 electrons, this gains 1 electron. We need to balance them up. How do we balance this? This equation with, since these are prime numbers, this one and this one is a prime number, this is supposed to be multiplied by 1, this is supposed to be multiplied by 2. Prime numbers are handled like this. For example, if this was 2 electrons and this was a gain of 2 electrons and then gain of 3 and a loss of 2 electrons, let's suppose it was something like this, then this was supposed to be multiplied by 3, this was supposed to be multiplied by 2. That's how it works with prime numbers. So in case of prime numbers, we actually multiply them each other by the smallest possible number so that we can make sure. So since this is 1, we don't need to do anything over here. We however multiply this equation by 2. That's the 2 over here. Now add the equations on both sides. This reactant over here, this reactant over here, left. Cancel out these two and this product over here, and of course this product over here. So you actually write all left things of the reaction on the left, the right on the right, and then you check the equation. Checking the equation, one nickel atom, two iron, whether those are atoms or ions, and something that is important, and you'll find it on both sides. Although you are done balancing the electrons on both sides, I hope you remember that this was 2 electrons, so was this, but you can always check zero oxidation state, 2 into plus 3, so 0 plus like this, and then this one is plus 2 and this one is 2 into plus 2. So you're going to find plus 6 over plus 6. Even the sum of oxidation states on both sides have been equal. So what we can do is that we can do this, make the electrons equal, add the stuff, and then just for a check, this works as a good check, the sum of the ions or the charges or oxidation states on both sides is going to be equal. This works as a really good check of what you have done is correct or not. So you actually are balancing the atoms as well as the charges on both the sides. Okay, let's do one more example so that you can understand what I've been talking about. Construct a balanced dynamic equation for iodide ions with manganese 7 ions in the presence of hydrogen ions. So we have iodide ions being converted into iodine, manganese ions in the presence of hydrogen work like this. They give us Mn plus 2 plus they give us 4 water. So check this out. You have 2 over here and 5 over here. So you multiply this equation by 5 and you multiply this equation by 2. Why? They're both prime numbers. So when you do this, this becomes like this becomes like this. Now we're going to add everything up. This on the left side, 1, 2, 3. This is going to get cancelled by this one. Let's talk about right hand side. 1, 2, then 3. There you go. You have everything over here. Now, as per my rule, let's go for a check. So this is 2 into -1 plus 10 into -1 plus 16 into +1 on one side. Let's do it on the other. 2 into +2 plus 5 into 0 plus 8 into 0. Since water and iodine are actually neutral species. So what's this going to be? This is -2 minus 10 plus 16 plus 4, and all of this is 0. The answer to this one is +4. The answer to this one is +4. Balance. Make sense?
Yes, sir.
All right. Ali, are we clear too?
Yes, sir.
Okay, good. So a few more questions are given for half equations. You can always construct these out, balance them. You know how to do it. Okay, moving on to the next portion, oxidation numbers. Now, what are oxidation numbers? We can extend our definition of redox even further to include oxidation, induction, reactions involving covalent compounds. We do this by using oxidation numbers. Oxidation numbers are also called as oxidation state. An oxidation number is a number given to each atom or ion in a compound that shows us its degree of oxidation. It may not be oxidized or reduced at all in a reaction. For example, in covalent bonding, they're simply sharing electrons. But oxidation numbers are more like fake numbers for valency. So they work in a very good way. Oxidation numbers can be positive, they can be negative, they can be zero, the plus and the minus sign, or it must always be included. So higher positive oxidation number means that the atom or ion is more oxidized. High negative, on the other hand, means it's more reduced. So you would know. Zero, while we are at it, represents nothing, not oxidized, neither reduced, neutral. Okay. For example, figure 7.2 shows magnesium oxidation number 0 attached to a hull of a ship. Now, it prevents the hull rusting by sacrificial protection. When it releases electron during this process, the oxidation number of magnesium changes from 0 in magnesium metal to +2, that is in magnesium ion. And that's a very good example. Now, this is a part of ship's hull. It is made up of iron, protected by bars of magnesium metal. Magnesium atoms have oxidation number 0. They oxidize to Mg2 positive, and they do so in preference to iron. This is sacrificial protection. We protect by sacrificing a more reactive metal. And as I've said, you can see in the example, and I hope you already probably know. Don't forget that we have studied this as a part of O level or IGCSE, that in case of more reactive metals, there was carbon, of course. Sorry, my bad. Moderately reactive, and then there was hydrogen. And then afterwards, we had copper, silver, gold, platinum as least reactive. You know, the magnesium comes over iron in this case. So of course, magnesium is more reactive, iron is less reactive. So magnesium is going to get oxidized when it is at a comparison or at a competition with iron. This is something that I've already explained. It's just that we're using this specific thing to our advantage in the name of sacrificial protection. I hope you get the example. Okay, moving on. There are a few set of rules that we define for oxidation number, and if you know and understand or remember these rules, oxidation numbers are never going to be difficult for you. Remember, in ionic bonding, we have the valencies. We already know how many electrons are gained or lost or transferred from one species to another, but oxidation numbers is like a bigger, broader category. So it also works with ionic compounds as their valencies and oxidation numbers are the same, and it works for covalent compounds as well because we give them fake numbers just to show how oxidized or how reduced can they be if we take them on the same scale as ionic compounds. So that's what it means. Oxidation number is sometimes also considered as an assumption for oxidation or reduction for covalent compounds, though they are sharing electrons and not exactly transferring electrons from one species to another. Now, important, the more positive or less negative the oxidation number, more oxidized a substance is, vice versa. The less positive or more negative the oxidation number is, the more reduced the substance is. Take care with negative oxidation numbers. Remember that an oxidation number of -3 is less oxidized or more reduced than an oxidation number of -2. For example, N -3 and O -2, when these two are compared, this means this is more reduced or less oxidized in comparison to this one. Okay, so these are the way we call them. Hopefully, you're gonna get better with this when we go through all the rules. Now, we can reduce oxidation number of an atom or an ion by oxidation number rules. It's important to know that the oxidation number rules refer to a single atom in a compound. Now, this always go for a single atom. Oxidation number of any uncombined element. Uncombined element is an element that does not combine with any other element. That's what uncombined element means. It may combine its own atoms. For example, S8 is actually a combination of all sulfur atoms. Cl2 is a combination of all chlorine atoms. O3 in ozone is a combination of all oxygen atoms. P4 in phosphorus is a combination of all phosphorus atoms. So oxidation numbers in each case would be 0, 0, 0, 0, which means noble gases are also 0. All the metals in their original states 0. That's why magnesium was 0 in the previous example. So these are all 0. No matter how many atoms were there in sulfur or in phosphorus or in oxygen or the single alone atoms, they're always 0. Okay. So moving on. In compounds, many atoms have ions have fixed oxidation number. For example, group 1 elements are always +1. Group 2 elements are always +2. Fluorine is always -1. Hydrogen is +1 always, except in metal hydrides, something like this, where it is -1. How would you know the word hydride would be quoted over there? Oxygen is -2 in normal oxides. In peroxide, the value is -1, and in OF2, it is +2. All right. There is a kind where we discuss super or suboxides. You're going to know about it in the papers. Don't worry. These are the simplest ones that we go with right now. Okay. So, how do you know in OF2O or OF2? It can be written both ways. Oxygen is +2. Why? Because fluorine always stays as -1. Why is fluorine always -1? Fluorine is the most electronegative element on the planet, and that gets to have the negative charge in comparison to any other. Now, I do understand that oxygen is the second most electronegative element on the planet, but when these two are in comparison, fluorine is going to win and have a negative charge. So, oxygen is bound to have a positive charge then, even for a compound between oxygen and fluorine only. And now you see the example. Now you know and understand what I'm talking about. Okay, the oxidation number of an element in a monoatomic ion is always the same as its charge, like its valency. So Cl minus means -1, Al plus is plus 3. So you understand that valencies for these kind of ions are equal. Now the sum of oxidation numbers in a compound is 0. This is something I specifically practice in O level. So I hope you understand what that means in A level. What that means actually is that you can always calculate something that you don't know about in a simplest exercise. For example, NO2, oxygen is -2 into 2. How would you know about this one? Put it as x, or you may put it as n. So x plus 2 into minus 2, as per this rule says, is equal to 0. So x plus, sorry, actually we should write it like this, is equal to 0, and x is equal to plus 4, which means nitrogen is equal to plus 4 in this case. That's how you know. Since you know the whole thing is going to be 0, so these and these are going to balance one another. And that's how if it's 2 into minus 2, this one, this entire, in its entirety becomes plus 4. Get the point?
Yes, sir.
Yes.
Okay, Ali, you are the one who is, I'm specifically targeting because I've done this practice in a very good way with Lab already. I gave her
Yeah, I'm
like
fine with this, sir.
15 to 20 different questions back in IGCSE, so I hope you're good. Okay, you're good. So when we talk about the sum of oxidation number in an ion is equal to its charge, let's consider another example then. In case of ions, let's suppose this is like this. Now we know oxygen is -2 and there are 4 atoms. Sulfur is something that we might need to find out. So let's consider it as S plus 4 into -2. And as per this specific value, it's equal to -2 actually. So S minus 8 is equal to -2, and S is equal to -2 plus 8, which is equal to plus 6. So sulfur over here exactly is plus 6. Now let me explain. Since all of these examples that like I was considering previously or these ones, these are actually covalently bonded species. And covalent bonding is actually a characteristic of a non-metal. So it means that non-metals are supposed to have two different characteristics. When they're forming ionic compounds, they actually come up with their valency. And valencies are pretty easy. Group 4 is plus 4, group 5 is -3, group 6 is -2, group 7 is -1, and group 8 or group 0 is actually equal to 0. This is valencies. These are for ionic compounds. But when non-metals try to go with covalent bonding, now you may talk about fluorine or oxygen being the most electronegative one, but you may need to find about a sulfur or for nitrogen or for other ones because these in different compounds, for example, nitrogen is different in NO, in N2O, in NO2, in N2O3, and in N2O5. You'll be astonished. It's plus 2 over here, it's plus 1 over here, it's plus 4 over here, it's plus 3 over here, it's plus 5 over here. So the same nitrogen atom in covalent bonding, since it can bond with a single bond or with a double bond or with a triple bond, or it may also go because of its lone pair for dative bonding, may have a different value in different formulae. That's what I've been trying to emphasize. So non-metals have the capacity or capability to show different oxidation states in different kind of covalent compounds. I hope with writing all of these examples, I clarify my point. Do I, Ali?
Yes, sir.
Good. So in either a compound or an ion, I'm going to move to the last point. The more electronegative element is given the negative oxidation state. So in case of comparison with nitrogen and oxygen, I have always been giving oxygen the negative oxidation state. Why? I already know on a scale, fluorine is the most electronegative one, then comes oxygen, then comes nitrogen, or then comes fluorine, so on and so forth. So I knew which one is more electronegative, and I have been giving it the negative oxidation number all along. So I've already been following the specific principle or rule. Okay. So moving on, applying the oxidation number rules, since we can easily practice this. N2O means Na is plus 2 or O is minus 2. And I hope you understand this way it works, the whole thing giving a zero value, or in case of Na2S, it's going to have the same thing. So this also gives you the idea that they have the same formula, their atoms are probably from the same group. They might end up in the same oxidation states, which in this case, oxygen and sulfur does. Compounds of metal with a non-metal, non-metal with a non-metal, covalent ones are important. So you can always come up with these examples and you can understand what we have been doing. I've already considered a few oxides of nitrogen to give you an idea about this. Compound ions. We have just discussed sulfate. If you go with nitrate, you'll know. If you practice all the compound ions, for example, HCO3 negative for C, CO3 negative 2 for C, NO3 negative for N, or SO4 negative 2 for S, or PO4 negative 3 for P, you're not never going to have problem with these. If you work them out just once by yourself, you'd know about their valencies and you won't have a problem. You'll notice that sulfur is capable of showing +2, +4, +6, apart from showing -2 for the covalent compound. Okay, -2 is something that it usually shows in any compound. Okay? So remember, the oxidation number refers to a single atom or ion in a compound. Single, not all. That's why whenever we go with something like this means for if I am calculating for this one and oxygen is -2 into 7 is equal to -2, the whole thing because of this charge. For sulfur, I am supposed to do it like this. I'm not supposed to do it S plus this because there are two sulfurs. So that way I'll always be doing it correctly. Okay. So if you look at it, it would be 2s equal to -2 plus 14. Then you are going to wind up with plus 12. That's how you will be able to come up that sulfur is plus 6 all around. This 2 is important. That's why he is doing something like this. So you would know that you don't skip this 2. The oxidation number of any element is 0 in these cases, in their original forms. Now, oxidation numbers are usually whole numbers, but there are cases where it appears to be fractions because the structure of the compound has not been taken into account. All right. So it is possible that as in fractions. I was talking about oxygen and I was talking about superoxides, and superoxides sometimes it may be like this. That is possible. All right. For example, a superoxide, KO2, has been discussed in A levels past papers. Now, K is always +1, which means oxygen here is -1/2. One atom of oxygen. Since there are two, the overall would be -1, and that's how these will balance. So superoxides, for specifically superoxides for oxygen, this is the value, and this actually helps with fractions. I'm giving you an example out of past papers. Okay, moving on. These are the questions, and you can always work out the oxidation number of bold atoms by a little bit of calculation. So moving on. Redox and oxidation numbers. Since oxidation is increase in oxidation number, I've already explained, and reduction is a decrease in oxidation number. So we will always be able to work it out. Just a second. Okay, so when tin reacts with nitric acid, the oxidation number of each atom of tin and nitrogen changes, and that's what has been shown over here. Now, in this specific case, the word each atom actually tells you that this how this whole thing has been worked out. There may be more than one atom in the equation, which in this specific equation is true for nitrogen, but they are only working with one atom at a time. That's how these values have been coded. For tin, you can see it's going from 0 to +4 in this case. How do we work it out? -2 into 2. Of course, the balancing number would be +4 to make the whole thing 0. Or again, -2 into 2. Again, this would be +4 in order to be balanced. And since you might already have worked nitrate ion out, you would already know nitrogen is +5 in nitrate ion. So you might need to recalculate the whole thing. Okay. So in this specific case, what's happening is tin is going with oxidation and nitrogen is going with reduction. What he's going to explain over here in these terms, in the opposite terms, the one that is going with oxidation is reducing agent, and the one we're going with reduction is oxidizing agent. So the whole species, nitric acid becomes the oxidizing agent, and tin becomes the reducing agent. Or nitrogen and the nitric acid becomes the oxidizing agent, and tin becomes the reducing agent. I hope you get the point. You can work either way of the perception, and that's fine. Okay. So moving on, oxidizing and reducing agents. Let's define these in order to be all on the same page. Oxidizing agent or oxidant, as we have the word we have used in common past papers, specifically the ones beyond 2014, okay, is a substance which brings about oxidation by removing electrons from another atom or ion, not itself, another atom or ion. So an oxidizing agent increases the oxidation number of another atom or ion. Okay. When this happens, the oxidation number of the oxidizing agent decreases. Typically, oxidizing agents are oxygen, fluorine, potassium manganate, potassium dichromate, ozone, air. You can actually extend the list with the kind of examples you have faced previously, or in the O levels or IGCSE, or in the previous parts of the same book. Okay, so oxygen, fluorine, potassium manganate, potassium dichromate, ozone, air, or the most reactive nonmetals are going to be very good oxidizing agents. Reducing agents or reductants. The substances that bring about reduction by donating or giving electrons to another atom or ion. A reducing agent decreases the oxidation number of another atom or ion. When this happens, the oxidation number of the reducing agent increases. Typically, reducing agents are hydrogen, potassium iodide, reactive metals such as aluminum, magnesium, calcium, sodium, potassium. All reactive metals are good reductants, just like all reactive non-metals were good oxidants. Since oxidation and reduction usually occur together, every redox reaction there must be an oxidizing or a reducing agent. For example, in the equation given below, MnO4 negative is the oxidizing agent, and Fe positive 2 is the reducing agent. Okay, this is because Mn decreases from +7 to +2, right? Or it has increased the oxidation state of iron from +2 to +3. Vice versa, for Fe's case, it increases from +2 to +3, or it has decreased the oxidation state of manganese in MnO4 from +2 to Mn2 +2 in manganese +2 to +2. Okay, so you should be able to come up with sentences like these, or you should be able to convert these sentences into numbers for your own understanding. So the ability of a substance to act as a good oxidizing or reducing agent really depends upon standard electrode potential, which we are going to do as a part of A2. Many substances can act as either good oxidizing or reducing agents depending on the substances they are reacting as well as the conditions. For example, hydrogen peroxide can act as a good oxidizing agent or a good reducing agent. Take the examples. For oxidizing agent, this is we have iron 2 positive ions and H positive. Okay. And for reducing agent, we have OH negative and iron 3 negative ions. In case of iron 3 negative, they are actually converting it into iron 2. In case of iron 2, it's actually converting it into iron 3. So yeah, some substances do have the capability to act as both, but that really depends upon what kind of competitor it has or what are the conditions. As you can see in both the reactions, if the competitor, my bad, if the competitor is over here is a species with less oxidation number and can move to a bigger one, and in the presence of an acid, it's acting like a good oxidizing agent. For something that has a higher valency and can move to a lower one, but cannot move to anything higher, in the case of alkaline conditions, it's working the other way. So I hope when we use the phrase as the conditions, acidic or alkaline, or what they are reacting with, like this. Okay, that's why he's considering both as factors, right? Probably the last stuff for today, naming compounds. Now we have been using this systematic naming technique, uh, a little bit of it back from IGCSE. We do know that we have been putting Roman numerals in parentheses next to the name of transition elements to show whether the transition element is making a +2 compound or a +3 compound, or what kind of oxidation state are they using. Okay, you have been familiar with this. But we also use oxidation numbers to distinguish between non-metal atoms in molecules and ions, because they might show valency in case of this and oxidation states in case of this. Okay. Well, however, we do use the term oxidation numbers or states for both of these as a bigger, broader term. So oxides of nitrogen. So I've discussed this example already. You already know about +1, +2, or +4. This is nitrogen 1 oxide, nitrogen 2 oxide, nitrogen 4 oxide. I've already explained that nitrogen 3 oxide exists, and even nitrogen 5 oxides also exist. Now you know. However, oxidation number of oxygen is generally -2. And when we talk about some ionic bonding, nitrogen actually acts as a nitride. But that is the case of iron. In all these cases, it's actually a molecule, covalent bonding. This also gives you the idea about bonding. That's actually a pretty good way to work it all the way around. Nitrate ions. Now, this is actually a difference between nitrate, we have been taught back in IGCSE, and nitrite. All right. This is something we are already done with, but different names. Here, we handle it like this: nitrate 3, nitrate 5. Because if you work out the oxidation states for NO2 negative, actually, this is a mistake in the book. It is supposed to be NO2 negative, like this, not NO negative 2, of course. This is +3 and this is +5. Okay. Note that the oxidation number comes after the ion it refers to. Okay. So, which means it's not sodium 3 nitrate, it's sodium nitrate 3. The name of ions containing oxygen and one other element end in ATE, but hydroxide ions OH negative are an exception to this rule. For example, ions containing fluorine and oxygen are fluorates, and ions containing sulfur and oxygen are sulfates. Name of inorganic acids containing oxygen end in IC. Roman numbers goes directly after the ion, contains the oxygen and another element. For example, H3PO3 is phosphoric 3 acid, H3PO4 is phosphoric 5 acid. That's how we work with. HClO4 is chloric 7 acid. All right. HClO3, HClO2, HClO also exist, so we can work out their states as well. So also common acids are usually named without the oxidation state of the non-metal ion. For example, this is going to be magnesium nitrate, not magnesium nitrate 5. This is potassium sulfate, not potassium sulfate 6, because these are the simplest examples. Note that we do not state the oxidation state oxidation number of the metal if it has only one oxidation state. So it's not potassium 1 sulfate, it's only potassium sulfate. It's not magnesium 2 nitrate 5, it's always magnesium nitrate, like this. Okay, so I hope you understand all the important points that are written over here. And they have shown you how that works. Sodium nitrite and sodium nitrate. In other words, sodium nitrate 3 and sodium nitrate 5, as written in proper names. These are known as systematic names. We also call them IUPAC names. Now, you can name, move from name to formula. Each unit of sodium chloride 5 contains one sodium ion. What is the formula of sodium chloride 5? So you can always work it out. Now we know sodium has +1 charge, oxygen has -2, chlorine has +5 as stated over here. So what would be the formula? NaClO3. Why O3? Because that's the only way we can balance out these two. The sum of these two are going to be +6. If we are supposed to go with -2, it can only be 3 in order to balance it with -6. So that 3 is written right over here with oxygen. That's how you work it out. Or you may work out like this way. So both of the perceptions are right. You can always work it out like this. Okay. There are some examples over here. Let me see about this one. I think this practical activity is too simple. You can read it later. I'm gonna just jump to balanced chemical equations using oxidation numbers. So what can you do about these equations? First of all, identify oxidation number changes, balance those oxidation number changes, then balance the charges, finally balance the atoms. We're going to work a few examples out. For example, copper 2 oxide reacts with ammonia to form copper, nitrogen, and water. Deduce the balanced chemical equation for this. Now, it's written like this. Now, this seems as a really simple equation. We might cheat into this and we might try to balance it other ways, but there are complicated equations in which this method works better and faster rather than just simply balancing them. Okay, so they have already worked out the oxidation numbers. If you look at the changes, you will finally understand that it's all about copper and nitrogen. Nothing is happening to hydrogen and oxygen. That's why copper and nitrogen are in red and not the rest. Now, copper is going from +2 to 0. Nitrogen is going from -3 to 0. Means one of them has a change of +3, one of them has a change of -2. Multiply the prime numbers with opposite numbers, +6, +6. So what do? We actually balanced out, used the numbers. Copper, that was with a change of 2, was written with 3 on both sides. Nitrogen was already mentioned as 2 over here, so balanced out by writing 2 over here. We were supposed to write 2 with both the nitrogens, but this was already 2, so we don't need to write 2 before it. Now, this is the step 3, where we actually balance the oxidation number changes. Okay, and the charges are balanced as well, -6 and -6. Okay, and that is the thing you have been explained over here. Then you can go with the rest of the equation and balance the atoms. You would notice that apart from these, we might need to put a 3 over here in order to balance the atoms. That is for the balancing of hydrogen and oxygen atoms. There you go. The entire equation is balanced. Let's do one more example. And this one is going to be pretty good with the stuff I was saying before, that if you try to balance this whole equation out in simple numbers, it becomes really, really difficult. So it's working this way is much better. Now manganese is going from +7 to +2, and iron is going from +2 to +3. There is a +1 step change with iron and -5 change with manganese. So we need to multiply 1 with 5 and 5 with 1, which means we do not need to multiply anything with the manganese equation. However, the iron's equation is multiplied by 5, and you see 5 over here and 5 over here. That's what we get. Now, you need to balance the charges. How can we do that? Initially, ignore the hydrogen ions, as they will be used to balance the charges. The total charge on other reactants is minus from MnO4, which is unfortunately not mentioned over here, negative from here, okay? And 5 into this from this one. We've ignored this intentionally and this. So the total of this is this. The total of this is this. So we need +8 on this side, hence this. We used this, we initially ignored this because we knew we're gonna use this to balance this, the whole stuff up. When you're done doing this, You can then use the numbers to balance out hydrogen and oxygen since there were no changes on these. Once you're done with this, actually you have balanced the whole equation out. Okay. Couple of times if you try to balance the equations for these reactions like the manganate reactions or the dichromate reactions, you're going to be good enough with these. Okay. Now, just a second. Let me see what do we have next. Should I go enough and finish this up too? I think it's too small. Let's do it. Disproportionation. So the element chlorine Cl2 has oxidation number 2 is equal to 0, undergoes a typical type of a redox reaction called disproportionation reaction when it reacts with alkali. Disproportionation can be thought of as self-reduction oxidation reaction, in which one single atom is going to be oxidized and reduced simultaneously in a reaction. There would be two changes occurring to the same atom. Let's take a look at this. When we add chlorine to cold aqueous sodium hydroxide, the following disproportionation reaction occurs. It moves from chlorine 0 to chlorine -1 and chlorine +1. Now imagine one chlorine atom gained an electron, the other chlorine atom lost an electron. Disproportionation. That's what this means. Okay. So the reduction reaction is like this. The oxidation reaction, half of this actually reacted with OH negative. Turned out this gives this. So one of them gained the electron while other one lost the electron. Okay. So he has mentioned both. The oxidation numbers are balanced so that equal number of moles of Cl negative and ClO negative in the equation that has already been worked out for you. Now the balancing equation involving disproportionation, when we add chlorine and hot concentrated aqueous sodium hydroxide, a different disproportionation reaction can take place. Instead of chlorate 5 ions, chloride ions, chlorate 5 ions, and water can be produced. So the point I'm trying to make is that we have cold aqueous over here, NaCl, NaClO, NH2O. Now take a look at the difference. When we are working out with hot concentrated, it's actually NaCl, NaClO3, and water. Okay, so balance the disproportionation reaction which takes place in chlorine is added to hot concentrated aqueous sodium hydroxide. The products are this ion, and water. We're only working with ions right now. Now, you write an unbalanced equation and identify the atoms that have a change in oxidation number. So oxidation number 0, OH negative works this way, +5. And the other one would obviously be the valencies, that is -1. One of them is -1, one of them is +5. So balance the oxidation number changes. So 1 and 5, opposite ones. So of course, we can do it like this. All right. I hope you get the point. So we started off with 6 chlorine, one of which converts to this, +5, and 5 of which, 5 into this would be -5. Actually, this balances out the whole thing. Now balance the charges on both the sides. Okay. Since we add 6 to it, it balances the whole thing. All right. This, I was talking about the state of chlorine over here and over here as a whole. This is the balancing for charges in species as a whole. This is -5, this is -1, this is 0, this is 0. This has to be 6 into -1 in order to be balanced out on both sides. This is what balancing the charges means. Do not confuse this step with the step for what I was saying. All right. So as soon as we balance the charges, we then go ahead with balancing the number of atoms. So we put a 3 with water in order to balance out hydrogen and oxygen, for which there were no changes. on. Okay, so hence we balance the whole thing up. And then we have a question about it too. You can always work with these questions, and there you go. The chapter is finished. Any questions?